Hello everyone, I welcome you all for this video. In this video, we are going to discuss about the numerical problems that is based on the material removal rate, feed rate, and the flow analysis. The theory part of this electrochemical machining processes we have discussed previously in the two videos, so you can go through that. So let's start the numerical problems. First is sorry. Okay, so this is the problem that has been asked previously in GATE examination 2009. So the electrochemical machining process is performed to remove the material and for an from an iron surface. The surface area of that is given, that is 20 by 20 mm square. Okay. The inter electrode gap, that is small h value, is given to you. The well supply voltage is given to you, that is 12 volt. Okay, the specific resistance of the electrolyte, that is small r, the value of the small r that is given to you is 2 ohm centimeter. Okay, the atomic weight, that is capital V, capital A, 55.85, and the valency V is 2. Now, in this question, this Faraday's constant value is given to you, so you have to take this value only in your numerical that formula. Okay, so that is 96,540. If it is not given, then we have to consider 96,500 only. Okay, the material removal rate we have to find out. So first of all, what the data that is given to you, we are writing that one, that is area of that cave or the surface area, that is 20 by 20. H, small h, V voltage, small r, that is specific resistance, atomic weight, density, valency, and the F. Okay, so how we calculate this MRR, that is I into A upon F into V. Now A is given to you, F is given, V is given, but I is not given. So for that I, we can take this formula as V by R. Okay, but V is given, R is not given. So for that R, uh, now this is a process that I is equals to V by R, and R is calculated as like small r, that is specific resistance, into H upon area between the gap. Okay, so this is formula that we are using for to calculate this capital R. Okay, so the small r is basically the specific resistance, that is in ohm centimeter, and H is in the minimum gap, that is mm, that is in mm. Okay, and area, surface area or the gap area, that is in mm square. So what we are doing is we are just converting this small r value, that is ohm in centimeter, into mm. So centimeter, 1 centimeter is equals to 10 mm. So I'm just writing or multiplying this value with the 10. So this will be 2 into 10 into h, that is 0.20, upon area, that is 20 into 20. Okay, so the unit is balanced. Now this will be 0.010 ohm. So now what we are doing is we are just putting this value into over this equation. So this will be I is equals to V by R. So the V is equals to 12 volt. So the 12 upon 0.20, so we'll get this value, that is 1200 ampere. So after getting this value, we'll put this value, whatever the value that is given to you or we calculated in this equation, and we'll get this I, that is 1200, A, that is 56 55.85, AF, that is 96,540, and V is 2. And when we will calculate, we'll get this value, that is 0.3471 gram per second. Okay, in gram per second only we have to calculate, so the option will be A. Okay, so this problem was asked in GATE 2009. So the uh, next problem is the electrochemical machining of an iron surface, and that is 25 by 25 mm square, using NaCl in water. Okay, so the second electrolyte that we used. Okay, the gap between the tool and the workpiece is this 0.25 mm, means the value of H is given to you, supply voltage, that is V, and specific resistance, that is 3 ohm centimeter. So the value of small r is given to you. Now estimate the material removal rate. Means up to this numerical, the same what we have discussed last numerical. Okay, so up to that is same, but in that next is feed rate we have to calculate, that is in mm per minute, and the electrolyte flow rate we have to calculate. Okay, for that the values is given to you, other values, that is Ce, that is specific heat, that is 997 calorie per gram into degree centigrade, and ambient temperature that is 35 degrees centigrade, and the boiling temperature that is 95 degrees centigrade that is given to you. Okay, apart from it, the density of the metal, that is iron, is given to you, that is 7860 kg per meter cube. Okay, so these are the data that is given to you. So I'm just writing over here in simple that what the data is given to you, so that will be for the better understanding. So again, up to the MRR, what we have done in the last numerical, we are doing the same. So this I, first of all, we are finding out, and for that we need this capital R value. So the capital R is equals to small r into h upon area of this gap. So all the values given to you. So I'm just putting these values. Please keep in mind that it is not 0.30, it is 3 only. Okay. So 3 into 10, again I'm converting this 3 ohm centimeter into ohm into mm. So the rest is same. The value of h, that is in mm, and the area of this gap, that is in mm square. So this is 25 into 25. Okay, so when you will calculate it, you will get this value as 0.012 ohm. Okay, so this is value of r. Now what we are doing is we are just putting this value into this equation, that is I is equals to v by r. So v is given to you, that is 12 volt, and r is that we have calculated. So this will be the current is 0. uh, Current will be 1000 ampere. Okay, so the next is we have to put this value in MRR equation. So this is 1000 into 56, that is a upon 96,500. Value is not given, so we are keeping this value as such. So a v is 2. So when you will calculate it, you will get this 0.290 gram per second. Okay, now first of all we are converting this into the kg per second, because this is MRR, because in it is asked in also in kg per second. So first of all we have to convert in kg per second. So when you will convert it into kg per second, so you have to multiply with the 10 raised to power minus 3. Okay, so this will be 0.290 into 10 raised to power minus 3 kg per second. Next is this is the answer, but what we have to do is in next we have to find out this value, that is feed rate. So the feed rate is equals to MRR upon surface area, or the area gap. Okay, so the MRR, the surface area is in square. So what we are doing is we should convert this value MRR from kg per second to meter cube per second, or cube per second. So that will be easy for to calculate this feed rate. Okay, so when you will convert this equation, so what we have to do, we have to divide this MRR by the density. So when you will divide it, like 7860 that is given to you for iron in kg per meter cube. So kg per meter cube, so the kg will be cancel out, and the final will MRR will be that is meter cube per second. Okay, now the feed rate will be equals to MRR upon surface area. So the surface area is given to you in square. So either what we can do is we can convert this meter cube into cube, or we can convert this square into meter square. So what I'm doing is I'm just converting this 25 into meter square. So that is 3 minus 3 means 1 meter is equals to 10 raised to power, sorry, 1 is equals to 10 raised to power minus 3. So that will be 10 raised to power minus 3 square. So that will be 10 raised to power minus 6. Okay, so this will be that will be in per second, per second. So I'm just when you will multiply it by 60, so that will convert in per minute. Okay, so this is basically the feed rate. Next is flow rate. So for the flow rate, you have to equal the heat generated, that or heat absorbed. Okay, so heat generated is I square R, and the heat absorbed by the electrolyte, that is Q into rho, that is not rho, basically this is rho E. Okay, of the electrolyte, density of the electrolyte, and Ce, that is specific heat, and Tb minus T naught, that is boiling temperature and ambient temperature. Okay, now the data all here I is given, we have already calculated, I R we have already calculated, Q we have to calculate, means this value we have to find out. Ce is given to you, Tb is given, T naught is given, but this density of this electrolyte is not given. So we have to consider this rho E is equals to 1 gram per cc. Okay, we are considering this value. 1 gram per cc. So when you will put this equation, also we have to keep in mind, because one more thing, that is ce, that is specific heat, but here the specific heat is given in calorie plus upon gram into degree centigrade. So that will be that calorie we have to convert. So when you will convert calorie into joule, so we have to keep 4.186 or 1187. Okay, so this value we have to multiply with 0 point with this value 0.997. Okay, so when you will convert it and you will put it values, so this will give you, so this is the conversion and this value we have to keep. So this I is 1000, r is 0.012, rho E is 1, and see that we are converting this value into joule. So 4.186 into 0.997 into TB, that is 95, minus T naught, that is 35. So when you will calculate it, this Q will be equals to 47.922 cc per second. Okay, so that is semi cube per second, because this density we are taking over here, that is in gram per cc. So the gram will be cancelled out and this cc will be in numerator. So this will be gram per cc per second. Okay, so this is the answer. Now next problem has been asked previously in gate 2008. Okay, so a researcher conduct electrochemical machining on a binary alloy. Now alloy is there, so the means workpiece material is alloy, and that is basically the binary alloy. Binary alloy means there are two metals, means one alloy is there, that is made up of the two different types of alloys, sorry, two different types of metals. Okay, so for that the but the overall density of this binary alloy is given to you. Okay, so the overall density of this binary alloy is given to you. So the density is n, if means density, that is 6000 kg per meter cube is given to you. Now one of them is iron. Okay, it's like this is one material, and assume that this is iron. Okay, so the atomic weight for this iron, that is 56, and the valency is 2. And another metal is p. So this metal, this part is any metal, that is p. For that the atomic weight is given, that is 24, and the valency is 4. Faraday's constant we have to consider, that is 96,500 coulomb per mole, and the volumetric material removal rate, means mrr, is also given, that is 50 mm cube per second. At the current I is also given, that is 2000 ampere. What we have to calculate is the percentage of the p metal in the alloy is closest to, means how much, means that alloy, means that both the metal, that is alloy that is made up of the both the metal, and how much percentage of that p alloy. So that we have to calculate when the mrr is this and the I is 2000. So what we have to do is the density of that is given, but the equivalency is different. So what the data is that is given to you, that is we are just writing over here. Okay, so the mrr will be equals to I into E, means generally what we are writing mrr value is I into A upon F, sorry, rho into F into V. Now this A and V values are different because it is a alloy. So that is that will be separate. We have to find out this E equivalent for both the condition, both the binary, means equivalent we have to find out. And density will be same, because overall density is given to you, that is 6000. Okay, so first of all what we have to calculate, that is rho, sorry, E equivalent. Okay, so E equivalent will be means 100 upon E equivalent into that formula I am using. So here only as binary alloy, so two terms we have to use, that is x1 and x2. Now what we are assuming is as we have to find out the percentage of the p metal p. Okay, in the alloy. So what we are assuming, that overall percentage, like if I am saying that overall the percent overall it is 1, then if means it is iron, there is iron, and this is p metal. So if I am saying that this the percentage of p metal is x percentage, then automatically what is of the iron, this will be 1 minus x. Okay, so means x1 percentage, I am just taking this term, first term, this is for iron, and this term, second term, for the p material. Okay, so automatically So if I'm taking this for iron, then x1, the value of x1 will be 1 minus x, and the value of x2 is x, because that is, I'm just considering that the x percentage of the p material in the alloy, and remaining is of iron, so that is 1 minus x. So when you will put this value, so this is for like two material, and when you will put this value of x fe, that is 1 minus x, and x for p material, that is x. Okay, what we have to do is, we have to put this value again, that is of that valency and this atomic weight of this fe and p. So when you will put these values, we'll get this e equivalence will be equals to 1 upon, as x is there. So when you will calculate it 2 by 56, there will be 0.05 0, this value will be come out 0.03571. So, and this same value will be multiplied with this x as well. So here it is plus and here it is minus, so there you will get it 0.13096 x. Okay, so the next is we have to put this value into mrr equation. So the next equation will be like mrr is equals to I into e equivalent upon rho equivalent into f. Okay, now V is not required, that is because we are writing E equivalent, and we do not have to calculate separate rho equivalent, because as I told you that the density of the binary alloy is given to you, means that is a combination of both the metal that is given to you, that is 6000. So there is no need to calculate separate. Okay, so when you will put this value, uh, this will be equals to MRR, that is given to you is 50. Now that is in mm cube per second. So what we are doing is, we are just converting it into meter cube, so that will be into 10 raised to power minus 9. Okay, now this I is 2000, that is given to you, that is 2000. And what we have calculated, that is E equals to 1 upon something like that. So this is 1 upon something, this value. Okay, so that is as such I'm just putting. And next is rho, density of the material, density of the alloy. So density of that alloy will be 6000 kg per meter cube. So same we are putting. Okay, so this just we are converting, because this value we have seen that this is in gram per second, because I told you in the beginning that this value we are considering in the gram per second, or in the, sorry, in the last video I told you that gram per second. So the, when you will convert this equation, this kg, so you have to convert it into grams, that will be 10 raised to power 10 raised to power 3, you have to write over here. So that is 10 raised to power 3. Okay, and the f value is 96500. So all the value we have already put. So when you will calculate it, and like these equations you will get in next step, and after that the percentage of x will be, means the value of will be 0.2548. So when you will convert it into the percentage, so you will get it around, it will be like 25.48, but as approximate value is given to you, because we have to set the find out the closest value. So this will be 25%. If we have to choose more greater one, but here it's 25 is given, so we'll take this one. Okay, so the answer will be B, that is 25 percentage. Okay, next is also one of the problem, that is a wonderful, that is, it's a very good problem here. The difference is we have to calculate the row density, row equivalence as well. Okay, so the things, that is composition of nickel superalloy that we are taking for the machining purpose, and the metals that is given to you are uh, nickel, that is 70%, chromium, that is 20%, fe, that is 5%. So 70 plus 20, that is 90, 90 plus 5, that is 95. So the remaining is titanium, so 5% is titanium. Okay, calculate the dissolution if the area of the tool is 1500 mm square, and the current is 1000 ampere is being passed through the cell. Okay, that EC cell only we are using, and the assume dissolution to take place at lowest valency of the element. So apart from it, the atomic weight and the density and the valency is given to you. Okay, so the same formula that we used in the last one, we use here as well. So these are the data that is given to you, Okay, first of all, what we means what the formula, that is MRR, because we have to calculate the feed rate, means the rate of dissolution means feed rate. So the feed rate will be equals to MRR upon surface area. But the first of all we have to calculate this MRR. So the MRR will be I into E equivalent upon uh, rho equivalent into F. Okay, there is no need to write V because we have already calculated in E equivalent. So first of all we have to I and F is given to you, and we already know F value. So I is given to you. We have to calculate this E equivalent and rho equivalent. Then we'll get this value of MRR. Okay. So what we are doing, first we are calculating this E equivalent. So E equivalent, the formula for that, that is 100 by uh, E equivalent equals to for the first composition, second composition, third composition, and so on. So, but here we are taking four composition, and so we have to write it accordingly. Okay. So this is for four composition. First composition for the nickel, second for chromium, third for iron, and fourth for titanium. Percentage is already known. Valency factor, valency is already given to you, or atomic weight is already given to you. Just put the value and get the value of E equivalent. Okay, so when you will put these values, E equivalent will be equals to 27.46. Okay, it's a very easy, just we have to calculate only. Okay, the next is the rho equivalent means density value. So that will be equals to 100 upon E equivalent, that is x1 by rho 1 plus x2 by rho 2 and so on. Here again four metals we are using, so this will be equals to up to 4. What means for the density for the first, second, third, fourth. Okay, now one more thing is that I have forget to mention this unit of this. So here it is given in gram per cc. Okay, this row. So when you will put these values, percentage is given, row is given, so just we have to put the value and calculate it. So this density will be 8.069 gram per cc. Now all the things we have, so first of all we are calculating this MRR. So the MRR will be equals to I, that is 1000, E equivalent, that is 27.46 upon density, that is 8.069 into 96,500. So now we are using this density, so the value will be the MRR will be in cc per second. Okay, so when you will calculate it, this value will be 0.03526 cc per second. Okay, so the what we have to find out, that rate of means feed rate we have to find out. So the area that is given to you of that tool is 50 100 mm square. So what we have to do, we have to convert this into this cc into mm square. Okay, and this second into the minutes. Okay, so that will give you the mm per minute. Okay, so the MRR will be equals to this when you will convert this into meter per minute, mm cube per minute. So this will be 2115.6. Okay, uh, next is feed rate will be equals to MRR upon surface area. So MRR we have already calculated from here, and the surface area is 1500 mm square. So we'll get this value as 1.4104 mm per minute. Okay, so these are the answer for that. Okay, next, thank you so much guys, we are stopping up to here. Thank you.